everyone, today we're working on question 9 on the 2022 Euclid. So this question says, suppose that m and n are positive integers with m is greater than or equal to 2. So the mn sawtooth sequence is a sequence of consecutive integers that start with 1 and has n teeth, where each tooth starts with 2, goes up to m, and goes back down to 1. So for example, this is the 3-4 sawtooth sequence. So it starts with 2 and it goes back down to 1. So this is what it looks like. Looks like a reversed check mark here. It goes up to m, which is 3 in this case, up to 3, and then back down to 1. So the 3-4 sawtooth sequence that we have here, there's 17 terms, and the average of the terms is 33 over 17. So there's 17 terms, and the sum of the terms is 33, so the average is 33 over 17. So first, for part A, we want to determine the sum of the terms for the 4-2 sawtooth sequence. So let's start with this. The 4-2 sawtooth sequence is pretty small, so we can just write it out. It's going to be 1, 2, 3, 4, 3, 2, 1, 2, 3, 4, 3, 2, 1. So we can just sum up. Let's highlight one of the sawtooths. So what is the sum of this orange highlighted section? Well, there's 4 plus 2 3s, that's 10, plus 2 2s, that's 14, plus 1, that's 15. So this orange highlighted section has a sum of 15. Note there's 2 identical highlighted sections, so that's 30, and then we have a 1 at the start. So it's going to be 15 plus 1, this is equal to 31. And that's the answer for part A here, 31. So oops, I wrote that on the B part. Okay, so this is 31. B, so for each positive integer m is greater than or equal to 2, determine a simplified expression for the sum of the terms in the m3 sawtooth sequence. Okay, so part B, so for any sawtooth sequence that goes up to n, m, it's going to be like 1, 2, ... all the way to m. Let's write m minus 1, m minus 1, ... back down to 2, 1. And then we'll repeat this. So 2, ... m minus 1, m minus 1, back down to 2, 1, and so on. So we want a m3 sawtooth sequence, which means we want to duplicate this highlighted section 3 times, and also plus 1. So our sum of this sequence is going to be 1 plus 3 times. So what is the sum of this orange highlighted area? Well, first we have 1 at the bottom here. We have m at the top. And we also have 2 of every other element. So there's 2 m minus 1s, there's 2 m minus 2s, and there's all the way until there's 2 2s. So 2 times 2 plus 3 plus all the way to plus m minus 1. So let's simplify this. So this sequence right here, this is a arithmetic sum, and the arithmetic sum formula is going to be the first number. So the first term plus the last term, 2 plus m minus 1, times the number of terms, so it's going to be m minus 1 terms, and divided by 2. So the 2's here can cancel out, and then let's just keep simplifying. 1 plus 3 times 1 plus m plus 1, m minus 2. So we'll bring out the terms in the m plus 1, m minus 2. That's going to give us plus m squared minus m minus 2. So these 2 plus m minus m will cancel out, and it's going to be 1 plus 3m squared minus 1. So this is the general formula for the sum of the terms, which is highlighted in yellow. And this is our answer for a m3 subsequence. So this is going to be 1 plus 3m squared minus 1. And it's in terms of m. So part C, we want to determine all pairs mn for which the sum of the terms in the mn sawtooth subsequence is 145. So we got the sum for the M3 subsequence. So for part C, we can just reuse this formula. So the sum will be equal to 1 plus, instead of 3, we're going to have a variable n. So it's 1 plus n times m squared minus 1. Okay, cool. So this thing is going to be equal to 145. We can move the 1 over. So that gives us n times m squared minus 1. This is going to equal to 144. So we know that 144 has a lot of factors, and one of those factors has to be a perfect square minus 1. So let's list out all the factors that 144 has. So it's divisible by 1, 2, 3, 4, not 5, 6, not 7, 8, 9, and 12. We stop at 12 because 144 is 12 squared. So if 144 divided by 1, that's going to be 144. Divided by 2, that's 72. Divided by 3, that's 48. Divided by 4, that's 36. Divided by 6 is 24. Divided by 8 is 18. Divided by 9 is 1, 6. Divided by 12 is just 12. So how many of these numbers is exactly 1 less than a perfect square? So 1 more than 1 is 2. That's not a perfect square. 1 more than 2 is 3. That's not a perfect square. 1 more than 3 is 4. So this is actually a valid perfect square. So if m squared minus 1, let's draw a table here. M squared minus 1, mn. So if m squared minus 1 is equal to 3, that means m is equal to 2, which means n is equal to 48. So that's a valid pair of positive m and n's. So going down the list, 4 plus 1 is 5, 6 plus 1 is 7, 8 plus 1 is 9. That's a perfect square. So m squared minus 1 could be 8, which means m is going to be equal to 3, and n is going to be equal to 18. So 9 plus 1 is 10, 12 plus 1 is 13. Those aren't perfect squares. 145 isn't, 73 isn't, 49 is actually a perfect square. So m squared minus 1 is 49. That means m is 7, and n is going to be 3. So 37 isn't, 25 is. So m squared minus 1 is 24. That means m is 5, and n is 6. So 19 isn't, 17 isn't, and 13 isn't. So all the pairs of m and n are here. We can just highlight these in yellow. So the pairs are going to be 2, 48, 3, 18, 7, 3, and 5, 6 for pairs m, n. So that's part C. That's all the possible pairs. There's no more factors of 144, and these are all the factors where one of the terms is equal to a perfect square for m minus 1. Okay, last part, moving on to part D. So prove that for all pairs of positive integers m and n with m is greater than or equal to 2, the average of the terms in the mn sawtooth subsequence is not an integer. Oh, sawtooth sequence. I don't know why I keep saying sawtooth subsequence. Okay, so this is not an integer. So we already have the formula for the sum. The sum is going to be equal to 1 plus n m squared minus 1. So we need the number of terms. So let's move back to the diagram we drew earlier here. So how many terms is in this orange highlighted area? Let's just do a different color so I can see. So in this orange highlight area, there's one term for the 1 at the bottom. There's one term for the m at the top. So that's 2. And then there's going to be 2 terms for every other term between m and 1. So how many terms are there between m minus 1 and... So how many terms are here, basically? So from 2 to m minus 1, that's going to be m minus 2 terms. So simplifying this is going to be equal to 2 plus 2m minus 4, or 2m minus 2. So the number of terms in the orange area is 2m minus 2. So the total number of terms is going to be 1 for the 1 at the start, plus n times, because there's n sawtooths, times 2m minus 2. So the number of terms is going to be equal to 1 plus n 2m minus 2. So the average of all the terms is just going to be these two, the sum divided by the number of terms. So this is equal to k. We want to prove that k cannot be an integer. So a common way to do these problems is to assume an incorrect statement. So let's assume k is an integer. So assume k is an integer, and we want to find a contradiction somehow. So we're not sure how to do that, so let's just try to simplify the equation here by bringing the base to the other side. So we have 1 plus nm squared minus 1. This is equal to k plus kn 2m minus 2. So let's just expand this. Nm squared minus n. This is equal to k plus k 2knm minus 2kn. Okay, let's bring all the terms onto one side so we can have a better picture of what's going on here. So it's nm squared minus 2knm, and then plus 1 minus n minus k and plus 2kn. So this is equal to 0. So this is actually a second degree polynomial if we treat our variable to be m. So a second degree polynomial can be solved with the quadratic formula. So we're going to have n. So these are the constants here. So this term is going to be a. This term is going to be b. And this term here is going to be c. So c, the constant. And this is the way we write the quadratic formula, am squared plus bm plus c. Okay, so in the quadratic formula, it's going to be negative b plus or minus b squared minus 4ac over 2a. So what we care about here is the determinant, or the thing that's under the square root here, because this whole thing is going to be equal to m, and m is a positive integer. That means this thing in here, called the determinant, has to be a perfect square. The determinant must be perfect square. Otherwise, there's no way for m to be an integer. So now, after that, all we care about is the determinant. So the determinant, this is going to be equal to negative b. So b squared, which is negative 2kn squared, minus 4a, which is n, and c, which is 1 minus n minus k, plus 2kn. So let's just expand the terms all here. We have 4k squared n squared minus 4n plus 4n squared plus 4nk minus 8kn squared. So now we can treat the variable to be n, and let's just group all like terms. So for example, n squares together and n's together. So we're going to have 4k squared n squared plus 4n squared, and then we're going to have, oh whoops, I missed the term minus 8kn squared. Okay, and then minus 4n plus 4nk. Let's factor out the common terms. So here we can factor out 4n squared. So 4n squared, k squared minus 2k plus 1, and minus 4, we should factor out 4n, so k minus 1. We just moved the negative sign inside the bracket and reversed. So instead of n1 minus k, it's k minus 1. So we notice that in the first part here, this is a perfect square. This is equal to k minus 1 squared. So using that knowledge, we can just factor that. So 4n squared, k minus 1 squared, plus 4n, k minus 1. So if we treat k minus 1 as the variable, we can see that this is almost a perfect square, because 4n squared, 4n, what we need is plus 1. So we can do a complete square here, which is plus 1 and then minus 1. So this entire thing here, this is going to equal to 2n k minus 1 plus 1 squared minus 1. Okay, so hopefully that made sense. We're basically factoring it and using complete the square. So now we got the determinant is equal to some term here. Let's call this term a squared minus 1. So the determinant equals to a squared minus 1. Remember we said that determinant must be a perfect square, right? The determinant must be a perfect square. That means, and a is a perfect square. So that means there's two perfect squares and they have a difference of 1. Determinant is 1 bigger than a. So are there perfect squares that have a difference of 1? Is that possible? Well, the perfect squares are going to be 1, 4, 9, 16, 25. Oh, I missed 0. 0, yes. So the only case where two perfect squares have a difference of 1 is 0 and 1, because otherwise the distance between the perfect squares keeps getting larger. So because this is the only set of two perfect squares that have a difference of 1, we know the determinant has to be equal to 1. Oh, sorry, it has to be equal to 0, and a has to be equal to 1. So 0 equals to a squared minus 1. So is that possible with the k's and n's we're given? That means a is equal to 1, so 2n k minus 1 plus 1 is equal to 1. Cancel out the 1s, or 2n k minus 1, this is equal to 0. So what does this mean? This means either n equals to 0 or k equals to 1. So is it possible for n to be 0? That's not possible, because we said in the question that, where does it say that? It says that m and n are positive integers, so n can't be 0, and also m is greater than or equal to 2. So n can't be 0. Is it possible for k to be equal to 1? If k is equal to 1, remember k is the average, or the sum of the terms divided by the number of terms. So if k equals to 1, the sum of the terms, which is 1 plus n, m squared minus 1, the sum of the terms, it has to equal the number of terms, which is 1 plus n, 2m minus 2. So is it possible that these two are equal to each other? This is the sum, this is the number of terms. Just move it down a little bit so it's easier to see. The 1's cancel out, so it's going to be n m squared minus 1 minus 2m plus 2 equals to 0. Simplify this a little bit. It's going to be m squared minus 2m minus 1 equals to n m squared minus 1 equals to 0. So we're seeing, is this possible? So for this to be possible, either n has to be equal to 0, or m has to be equal to -1, or m has to be equal to 1. So we already established n can't be 0, m and n are positive integers, so m can't be -1, and the question also says m is greater than or equal to 2, so m can't be equal to 1. So this is not possible. So the fact that this is not possible, this means k is not equal to 1. K equals to 1 is not possible. So this means that we already know that n can't be 0. So these two perfect squares can't have a difference of 1. So if all of this is not possible, the fact that k isn't equal to 1 means that determinant is not a perfect square. Or it cannot be a perfect square. There's no possible arrangements of m, n, and k. So if the determinant is not a perfect square, remember the determinant is used to solve for m in the quadratic formula. So that means m is not an integer. So m is not an integer. This actually contradicts what the question says, because it says m and n are positive integers. So we have a contradiction. So what is this contradicting? This is contradicting the statement that we said at the start of the question, which is assume k is an integer. So because we have a contradiction, k cannot be an integer, and we've proved by contradiction that k is not an integer. So k, that means k is not integer. So that's it for question 9 on the Euclid 2022. Hopefully you enjoyed the video, and thank you guys for watching.